Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available. All right, today we're hosting Prateek Jain from Penn State. Prateek has done some really interesting work on differential privacy. He just had 2 papers in Cult, which is really, really awesome. And he's going to tell us a grand view of all of this work today.
Good morning, I'm Prateek Jain from Penn State, and I'm going to talk about differentially private empirical risk minimization and high dimensional regression. It is a joint work with Prateek Jain from MSR India, Daniel Kifer from Penn State, Pravesh Kothari from UT Austin, and Adam Smith from Penn State. So this talk is essentially a merging of 2 different papers which I had in court, and let me try to give a high-level overview of it. So the primary intention of this work was to design learning algorithms with rigorous privacy guarantees. So before going forward, let's try to understand what kind of privacy guarantees are you looking at. Suppose you have a data set of a bunch of individuals. You can think each of the entry in the data set to be some kind of sensitive information about the individual. For example, it might contain information of bunch of his medical tests and a bit which tells whether he has AIDS or not. And you have an algorithm which is sitting in front of this data set, which is releasing summary statistic about the data set. For example, it might release a classifier to the external world to classify a person whether he will have an AIDS or not. So the summary statistic which goes out, you might think that this statistic goes to an adversary who has the intention of breaching the privacy of the dataset. Now by breach of privacy, I mean he might want to get specific information about a particular individual in the dataset. So thinking more about it, there are essentially 2 conflicting goals here. First, you want to release this kind of aggregate statistics to the external world because they are just useful. Additionally, there is this privacy concern that when you are releasing this aggregate statistic, it might reveal information about the individuals, and which is clearly a issue. And it so happens that this is a pretty difficult problem. Recently, there has been work where people design systems with some ad hoc notions of privacy, and there has been a lot of high-profile breaches against those systems. To name some of them, there was this work by Arvind Narayanan and Vitaliy Shmanikov, where they de-anonymized the Netflix price database, which essentially Netflix said that they have anonymized it and they are preserving the privacy of people. Then there was this work by Alexandra Korolova in 2011, where she showed vulnerabilities in the Facebook advertisement system. And there was a current work in Oakland last year where people showed privacy breaches against recommendation systems. So it's really, the question really arises is, what kind of privacy guarantees these ad hoc systems give? Or do we need to significantly rethink the problem? So in the last 3 to 4 years, people have been trying to design algorithms with rigorous privacy guarantees. And this has been an active area of research almost spanning across computer science: databases, learning theory, programming languages, cryptography, algorithms, just to name a few. So what I will do is in this talk, I'll narrow my scope down a bit. For learning algorithms, I'll specifically talk about empirical risk minimizers. And for privacy guarantee, I will use this notion called as differential privacy, which has been reasonably successful in the recent past. And this is one of the rigorous notions of privacy. Just to get a hang of what empirical risk minimization is, you have a data set of endpoints, and you are trying to get a model parameter which minimizes an empirical risk. Now, what is an empirical risk? For each of the data points for a given model parameter, you have a loss function L, which will give you the risk for that data point. An empirical risk is the average of the risk over all these data points. And for purpose of this talk, we will be thinking of this loss function to be convex in its first parameter. This is just for technical reasons. And an empirical risk minimizer is a model parameter which minimizes the empirical risk. Additionally, you add that term, that is a regularizer, to inculcate your prior belief about the minimizer. So for example, if you think that the minimizer had very few non-zero entries, the minimizer which you are trying to learn has very few non-zero entries, you might put a L1 regularization here. So this is essentially inculcating your prior belief about the system. Throughout the talk, I will be basically making references to the specific form of linear regression problem, that is this linear regression. It is one of the ERM problems which is pretty common. And some of the other empirical risk minimizers which I will be telling you over and all whenever like situations arise are this logistic regression, median, support vector machines, etc. Now, after having thought about empirical risk minimization and me defining it what empirical risk minimization is, the question arises, what kind of privacy threats does it pose? I mean, is it even worthwhile to investigate on designing private algorithms for empirical risk minimization? Consider this very simple and toy example. You have a data set of 5 points, -5, -2, -1, 2 and 5. And if I tell you find out the median of this data set, it is very trivial to see that -1 is the median. Now, you can write this problem of finding out the median as the empirical risk minimization problem. This is essentially minimizing over the parameter theta the sum of the absolute distances from each of the data points. And if you plot the graph of this function, it will look something like this. So it is the slope is -1, +1, +3, and -1, -3, -5, and the median is this guy.
You're actually computing the average, right?
No, I'm computing the median here. So the slopes are, so if you plot this graph, this is median. Average will be theta minus di square. That is average. So thinking of it, median is an empirical risk minimization problem, and you are revealing one data point exactly. And if your purpose was to protect the privacy of the data point, this is not a good news. And if this thing seems like a trivial problem, like I'm dealing with one dimensions, let me give you a more concrete problem. Support vector machines. Suppose you are dealing with support vector machines in its dual form, where you are outputting the support vectors. If you think about it, the support vectors which you are outputting are essentially the data points on the margin. And these support vectors are reasonably high dimensional. So you are actually revealing a lot of information about individuals. So with this kind of issues with empirical risk minimization, the question arises, what can you do about it? So these are the problems, and we need to mitigate these problems. So to that end, we use this notion called as differential privacy. It was initially proposed by Dwork, McSherry, Nissim, and Smith in 2006, and there was a follow-up work by Dwork et al. In 2006. So at a high level, what this definition tells you is that suppose I'm releasing an aggregate statistic about a data set. The privacy breach on you, the statistic can have, is independent of you being in the data set or not. For example, to be more concrete, suppose you have two data sets, D and D prime. This third entry is your entry, and that in the other data set, you have changed your entry to something else. And the algorithm is running on either on D or on D prime. Now the output is given to an adversary. Now the adversary cannot decide whether the algorithm was running on dataset D or D prime. To formalize this, a randomized algorithm A is epsilon delta differentially private. So epsilon and delta are the privacy parameters. So lower the values of epsilon delta, better privacy guarantees you have. For all datasets D and D prime that differ in one element, and for all possible sets of answers S, the probability that the algorithm running on dataset D produces something in S, and the probability that the algorithm running on dataset D prime produces something in S are closed by this factor of e to the power of epsilon and delta. So if you have seen this definition, it's good. If you haven't, it's fine. You don't need to remember the details of the definition. Only thing you need to remember that epsilon delta privacy parameters, lower value, better it is. Any questions so far? You sure?
Go back to previous slides. I just don't understand why solving this SVM will reveals the privacy of some people.
So if you're running SVM, so if you're running in its dual form, where you are outputting the support vectors, what are support vectors? Support vectors are the feature vectors, some of the feature vectors. And these feature vectors can be some of the individual information. For example, in the initial setting I told you, right, it might be a bunch of medical tests which you have done. And the final thing is whether you have it.
It's coming from these support vectors.
Yes.
I see.
So, yeah, so this is the definition of differential privacy. So let me try to motivate this definition a bit, why we have chosen this definition. So why is it a good definition? So one of the key features of differential privacy is this: they have this property called composition. What composition tells is, suppose you have this data set, I'm running two algorithms on the dataset. Algorithm 1, which guarantees epsilon delta differential privacy, and algorithm 2, which I'm running again on the dataset, which also guarantees epsilon delta differential privacy. Now, so each of these algorithms reveals something about the dataset. I mean, it doesn't. I mean, it doesn't give out zero information. So now the question arises: when I group these two information together, what is the privacy guarantee I have? Differential privacy trivially tells you that you will have 2 epsilon comma 2 delta differential privacy. Now, to my knowledge, this is the only definition, only rigorous definition which guarantees you composition so easily. There are other rigorous other definitions of privacy like natural differential privacy or noiseless database privacy. Getting a composition result of this clean form is very difficult. So this is one of the key features of differential privacy. And additionally, it gives you guarantees against arbitrary auxiliary information. So if you remember in the definition, I never mentioned about anything about auxiliary information. So I mean, I assume the adversary might know everything excepting your entry. However, what it does not imply. So recently there have been a lot of works where people kind of misinterpret or overinterpret this definition. It does not protect you against the information an adversary can learn from an aggregate statistic. For example, suppose someone runs a survey which tells that people who smokes have cancer. Now, someone sees you outside smoking, and from the survey result that smoking causes cancer, the guy who sees you smoking might have significant higher belief that you smoke, you have cancer. But this is independent of the fact you being in the dataset or not. So this might be a privacy breach, this might not be, but differential privacy does not protect you against this. And this distinction is pretty important.
Does that mean that the differential privacy cannot prevent you from getting the auxiliary information? So is that what this means?
So this means that the public information what is there, if that breaches your privacy, that differential privacy does not protect you against. For what it only protects you against is the computation which the system is doing for releasing that information, that is independent of you being in there. So yeah. So this talk is essentially about empirical risk minimization and how do you design differentially private algorithms for empirical risk minimization. So I'll be segregating the talk into two parts. One is in the low dimension, another is in the high dimension. By low dimension, I mean the number of sample points or the number of data points you have is much larger than the dimensionality of the model parameter. So the theta which I was trying to learn, the dimensionality of the model parameter is smaller than the number of samples you have. The other setting I'll be talking about is the high dimension, where the other thing is happening, where the dimensionality of the problem is much larger, maybe exponential in the number of sample parameter points you have. In the low dimension, I'll be initially talking about some of the existing work. This output perturbation, this was initially proposed by Chaudhuri et al. In 2011, and there was a follow-up work by Rubinstein et al. In 2011. Then I'll be talking about another technique called objective perturbation, which is in the same paper of the CMS 11, and then one of our recent papers where we make a significant enhancement to this objective perturbation. The third thing is using online learning techniques for guaranteeing differential privacy, and this is work by Prateek Jain, Pravesh, Kothari, and me. Then I want to kind of compare all these three approaches and see which one is better. Not that I have a very good answer right now of like how those pieces fit together, but there are some initial directions which I can tell like which one is better and why it is better. Sure.
So along with the outputs and the objective, isn't there also the possibility of perturbing the data points themselves to create false data that's
sure. So yeah, so the reason I didn't put was in some sense intentional. So what you are doing when you are perturbing the data points, so differential privacy in some sense needs that use of one data point is hidden from the output. Now if you want to perturb all the data points initially without looking what algorithm you're running, that essentially means that the effect of the data point is almost gone. For example, if you suppose let's take this example of averaging a bunch of numbers. You want to average a bunch of numbers. Now one way, and the numbers are bits, let's say. So the average can change by changing one of the entries 1 by n. So in the output if you add, you will be adding noise in the order of 1 by n. But if you are adding noise to the inputs, you'll be adding noise of order of 1 to each of the inputs. So when you take the average, there'll be an error of 1 by root n, because errors cancel out and 1 by root n. So there is a significantly higher amount of error in the input perturbation.
But you could find a solution. So in your support vector machine example, for instance, you could find a solution, and then you could say that, like, well, I'll perturb data points in the neighborhood and then find something which comes closer.
Yes, so that approach is somehow kind of related to this output perturbation.
Oh, okay.
It's like in the similar flavor. So output perturbation essentially, like, you use the structure of the problem a bit. So in high dimensional setting, the dimensionality of the problem is much larger than the number of samples you have, and this kind of problems are really hard to address, because even non-privately these are very hard to address, because the system remains extremely underdetermined with the number of samples. And what we do is we give private algorithms for sparse regression. So what sparse regression meaning, that the underlying model parameter which you are trying to learn from high dimensional algorithms, that model parameter has very few non-zero entries. Then you can do something interesting, and I'll tell how. So this first 2 bullets are mostly for batch empirical risk minimization, where you have all the sample points in one go. Now suppose you are dealing with advertisement systems or any kind of system which kind of changes over time. So you do not have the complete data set of hand. So that brings us to this online empirical risk minimization problem, where the data points are coming to you online. And the challenges here is much different from the batch setting, because in the batch you are somehow outputting only one output. But in the online case, every time a data point comes, you have to give some output, and the number of outputs is almost equal to the number of inputs you have, and this is a significant challenge in terms of protecting the privacy. So there we give a very generic technique for designing differentially private online learning. So this is our work, the other paper. So coming to batch empirical risk minimization in low dimension, there are 3 algorithms I will talk about. One is this output perturbation, objective perturbation, and online convex programming based. And then I will compare the 3. So output perturbation was proposed by Chaudhuri et al. So the idea of output perturbation is, first you select a random variable b from gamma distribution, where the scale of the distribution, it's a mean zero distribution, with the scale is order of 1 by epsilon. Epsilon is a privacy parameter. And what you do is then, you take your objective function of the original empirical risk minimization, find out the minimizer. Then you add this noise to it. So if you look at this picture, this is your theta hat, which has this 0 slope, and you add noise to it. And the claim is that this guy is differentially private. But for full disclosure, let me tell you that actual algorithm has is slightly different and slightly more tricky. But for the purpose of this talk, I think this is fine. So basically find out the minimizer and add noise to it. So the privacy guarantees, this algorithm is epsilon comma 0 differentially private, so the delta term is 0 there. And in terms of utility, the price you pay for privacy, so this is the loss with the empirical risk without the privacy requirement, and this is with the privacy. So the loss you pay is around p log p by epsilon n. So this zeta term is showing up there, it is the bound on the gradient of the loss, small little loss functions, and theta is the L2 norm of the theta. So these 2 parameters you can ignore for the purpose of this talk, because in all the guarantees I will show, we'll have this term common. So essentially what you need to compare is p log p by epsilon n. So essentially we have a dependence on the dimensionality as p log p, and n is the number of samples we have. Great. So the one issue with this kind of an approach is the privacy argument requires that you reach the true optima of the objective function. So the privacy guarantee is only for the true optima, if you reach the optima. Now in practice you might not, and it so happens the guarantees do not hold, or the analysis doesn't go through. So this is a significant problem in practice. In practice, what does it even mean to guarantee privacy for this kind of settings? And over a sequence of slides, I will show you how do you mitigate this issue. So the other algorithm is this objective perturbation. So I will mention this objective perturbation as objective perturbation of CMS, because we make an enhancement over it. So I'll just tell this is what CMS did. So what does this algorithm? Again, sample a random variable b from gamma distribution, and this time instead of adding noise to the output, what you do is you add a random linear term to the objective function. So you can think of this problem, think of the setting as 2 things. First, you take the objective function and randomly tilt it. Alternatively, So this was your original theta hat, which was for the loss plus the regularizer. What you are doing here is you're finding out a model parameter where the gradient of the objective function is equal to minus b. So if you are converse into differential duality, this is essentially working in the dual space, differential dual space. But we need not go there. Again, this is a simplistic view I'm giving you because you need to choose the regularizer in a proper manner to make things work out, but that's fine. So the result that was existent in objective perturbation, it required the space over which you are optimizing to be unconstrained. You cannot put hard constraints on this set. This has to be R to the power of p. And this rules out problems like linear regression for technical reasons, because to bound certain parameters for privacy, you need to work with the constraint state in the case of linear regression. Additionally, they required the regularizer to be smooth, smooth meaning twice differentiable. At least the analysis required it. So this essentially rules out most common regularizers like L1 regularization or nuclear norm, etc. So what we do is we allow convex constraints, we allow constraint optimization and non-differentiable regularizers. So to do this, we actually needed a significantly different approach which was analyzed earlier, and I will tell you what this approach is. It's completely different from what has been analyzed in the past. And the second contribution was we noticed that if we use Gaussian noise instead of gamma noise, because Gaussian noise is more tied to the mean, we can get a factor of root p improvement in the error. So earlier it was p log p, we can get root p in the error. And another thing which you noticed was this objective perturbation somehow respects the structure of the problem more. So if we give a tighter analysis, we have a tighter analysis which saves another factor of root p in the error. Sure.
So I don't understand the first statement, because it seems like if you're using linear regression instead of SVM regression, wouldn't it be inherently private because you're not exposing any data features to any specific data points?
So the idea about privacy is that, so the kind of privacy guarantees we are working with is a probabilistic guarantee. So the first point is no deterministic algorithm can satisfy differential privacy. So you need randomization. So the point is this: suppose my algorithm running on database D produces an output O. If I change O to D to D prime, since my algorithm is dependent on the dataset, any non-trivial algorithm should change its output. So the probabilities are now like one guy has 0 probability, another guy has 1 probabilities, and that basically essentially will not get this epsilon. So yeah, so and coming to this problem of linear regression, the specific reason we need this constraint set is if you take the gradient of the loss for linear regression, the gradient has the theta parameter there, and theta is the model parameter. So gradient is like x transpose y minus x transpose theta. So, and for privacy guarantees we need to bound the gradient, and you cannot bound the gradient unless you have bound on the constraint set. For logistic regression this is not the case, because you basically the differential of the logistic function, loss function, is the logistic function, and that is bounded by plus or minus 1 always. So yeah. So these are our contributions. Now coming to the guarantees, what we get epsilon delta differentially privacy, and the utility guarantees we get, now we lose a factor of log p, so the log p goes away, and instead of p we get a root p here, but we pay a per price in terms of privacy with the delta coming up, so there is not a 0 delta, so this is log 1 by delta, which is fine. And as I told you, we can make further improvements on the dimensionality for nice data sets, where essentially if the data set has some nice properties, then we can get better utility guarantees, so we can further reduce the dimensionality problem. Yeah, so coming back to the contributions, so I will not talk about these two parts, but what I will tell you is how do you relax, and this is in some sense the most interesting part of the work. So recall that if the regularizer were not differentiable, you will have your objective function something like this, and let's say this is the point of non-differentiability, and additionally to work with the constraint set you have a constraint here. So this is just denoting the constraint, so the objective function can be outside the constraints. What you do is for the regularizer we get a sequence of smooth approximations of the regularizer. So I'll tell you how you get the smooth approximations, but so for the non-differentiable regularizer I take, and I get a sequence of smooth approximations where each of the approximation is twice differentiable, and finally in the limit I converge to the actual regularizer. Additionally, what you do is, so with this sequence of approximation, the objective function will look like this because you have a smoothened out here, and slowly as I goes to infinity, this will start looking like this objective function. Additionally, we add a convex penalty term which penalizes the function heavily when you go out of the constraint set. Great. So there are like two significant challenges in finding out this regularizer, and it took like reasonable time for us to find out what is the way of doing it. So we needed to keep the strong convexity property of the algorithm unchanged. So if the limiting algorithm has some form of strong convexity, we needed to keep it unchanged, otherwise privacy guarantees get a hit. And the second challenge was we needed to find out the right notion of convergence. So let me tell you how do you even do the smooth approximation so that we satisfy both these challenges. So the first thing we do is we take the regularizer and convolve it with a smooth kernel. So you can think of convolving with a Gaussian kernel. And what we do is we reduce the width of the kernel as we go forward. And theorems from convolution tells me that if my kernel is twice differentiable or infinitely differentiable, my convolve function is also differentiable. But if your regularizer is non-differentiable in the limit, this guy is also converging to it, because when you are kind of shrinking the width of the Gaussian kernel from which you are convolving it, in the limit you will get a delta function, and convolving with the delta function is the function itself. So in limit you recover the actual regularizer. And we add a convex penalty term f of theta. Trust me, this is convex. That if you go out of the set, you basically make it pay. And essentially what you do is when you add in the approximations, we add the approximation pointer some I into the convex penalty, so that as I goes to infinity, it starts penalizing you heavily when you go out of the convex set. Coming to the second challenge, we needed a right notion of convergence. So I can show you something here. So you can think of this algorithm as some kind of a function which takes two parameters: the random variable, the noise, and the dataset D. What I'm doing is I'm approximating this function with sequence of f1, fk. One of the classic ways of proving this kind of results is going via convergence in distribution, saying that these two functions converge in distribution. So as I tends to infinity, you want to say that these two converge in distribution, which it does not happen here. Because if you see, let's say we are dealing with L1 regularization. In L1 regularization, there is no, based on this B, there is no density function there, because at the point of non-differentiability, we will have probability mass. So convergence of distribution doesn't hold. So what we need is we prove a weak convergence in measure. So roughly what we say is, so if you remember, here we need to recall differential privacy a bit. So in differential privacy, we give guarantees over probability measures of different output sets. What weak convergence in measure tells you is that roughly the argument goes like this: suppose my limiting algorithm were not differentially private. Limiting algorithm, so limit I tends to infinity, f of I is not differentially private. But I know that with the smooth approximations, all this sequence of algorithms are differentially private. So the argument is, if the limit is not differentially private, then there must be an algorithm in the sequence which is not differentially private. So this takes the contrapositive and proves that it's a contradiction, because if the limit is differentially private, then it's not differentially private, then there must be an algorithm which is not differentially private in the sequence, but already you have argued that the sequence is differentially private because it's a smooth approximations. Questions? Yes, so it's important to digest this part. Great. So essentially, yeah. So in the next step, what we show is we show a sequential closure of differential privacy. So this is a theorem which is kind of an independent interest. So what it says is, suppose you have a sequence of algorithms A1, A2, blah blah blah, all of them are epsilon delta differentially private algorithm. Then there exists a algorithm, and there exists an algorithm A such that for all data sets D and the algorithms AI converges weakly to A. When I say weakly, it converges pointwise. So if you get a pointwise convergence of these algorithms to A, additionally each of these algorithms are differentially private, then the limiting algorithm is also epsilon delta differentially private. So what it says is, suppose you have this A1, A2, blah blah blah, which limit converges to AI, then the complete block is differentially private. Yeah, so this is one of our theorems which we used for proving this property. Now after having talked about output perturbation, where you basically perturb the output, and then the other case where you tilt the objective function and solve, that is this objective perturbation, let me give you a significantly different approach from other two. So this is based on online convex programming, so you will be using online learning techniques to solve this problem. Just to give a background of what online convex programming is, you can think of online convex programming to be in this setting. It's an end round game between two parties. There is a player and the challenger. In each round, what the player does is it chooses a point in theta I, which lies in some convex set, and the challenger, based on seeing his point which he has chosen, he gives him back a cost function Li, and the player has to pay cost of Li of theta I. So this is a player versus challenger kind of a game, and the player wants to perform well. That means he doesn't want to pay too much of cost, and an online convex programming algorithm is such which gives a strategy to the player to choose these points. And the property you want from the online convex programming algorithm is that the regret, I will tell what the regret is, that should go down to 0 as you play more and more. So the idea of a regret is, so Li theta is the parameter which the player is outputting based on the algorithm. So this is the average cost which the guy pays, minus, suppose this person knew all the cost functions at once, then what was the best theta he could have chosen? So this is called the offline best. So you want to perform well against the offline best. That means as you see more and more samples, you want to go closer and closer to the offline best. So this is what any good online convex programming algorithm will give you, and this is what they call a sublinear regret. So you want to minimize the regret. Great. Now how do you use this framework for solving our differential privacy algorithm? So this cost functions you can think of to be this risk functions for each of the data points, L of theta of di. Additionally, we need this property from an online convex programming algorithm that it is stable. By stability I mean that you take two data sets D and D prime which differ in exactly one entry, and the ith iterate, the ith output which the player is outputting, the L2 distance between theta I on D and D prime should go down as 1 by I. So as you go farther and farther down the time, dependence on one single data point reduces linearly, and this is a property I need, and we call this thing as stable algorithm. Additionally, we want the original OCP algorithm A to be having sublinear regret, meaning that the regret should go down to 0 as n goes to infinity. With these two properties we can do something interesting. What you do is, we do this thing, this is a pretty common thing now in online learning, to use this online to batch conversion. So what you do is, you run the online convex programming algorithm with the loss function and appropriately chosen regularizer. So the OCP algorithm gives you a sequence of outputs, theta 1 to theta n. What you do is, you take the average of all these outputs, add a noise which is scaled roughly around p upon n square. The variance is p upon n square. So this is a Gaussian random variable. This has the similar flavor of output perturbation where you take the output and add noise. So this looks very similar to that, but this has much significant advantage over output. I will tell you why. First, and before going there, let me tell you this, that I told you we need stable online convex programming algorithms. Now, does there exist stable online convex programming algorithms in the literature? This is the first question you want to ask. What we show is, in fact, it is still not clear to us why it is happening. Every online convex programming algorithm which you picked up satisfies stability property what you wanted. each and every algorithm what you picked up. More precisely, this algorithm implicit gradient descent had this stability property. The GIGA algorithm by Martin Zienkiewicz in 2003 has this property conditioned on the fact that the cost function is differentiable. But I'm not sure it is a quirk of the proof or we actually need this. But anyways, so then follow the leader, follow the regularized leader, all of them have this property. Yeah, sure.
The stability property just says that you don't change your output too much based on a single
data point
difference.
No, it more tells you something more. So as you go farther in time, the change that can have that grows down with the time. So this goes down as 1 by I. So essentially you want to say that the last point which you're outputting almost does not depend on your sample set. So as I transmitted, this guy goes to 0.
The difference between two data sets gets
Yes.
washed out of
Yes.
the-
So I mean, at a very high level, what this guy is saying is, the purpose of a learning algorithm is to get something which I can use on a new sample point. In that sense, I should not be too much boiled down with one data point. And this is essentially telling that I should not overfit on one data point. Although it is not clear and it's an open problem kind of, that is there something fundamental closeness that is going on, and we can say that probably any algorithm that is differentially private has sublinear regret or the vice versa. I don't know. So what we show is our OCP algorithm is epsilon delta differentially private. The utility guarantee is very similar to objective perturbation, except in the fact that we get this polylog n term for technical reasons, but that is fine because sample size, logarithm in sample size is fine. The key property of this algorithm and why you looked at this algorithm is it is much more practical than objective and output. If you see the privacy guarantee, it does not really depend on you minimizing any objective function. The OCP algorithm essentially works by gradient descent, and your algorithm, what you are outputting, is essentially taking an average and adding noise to it. So the privacy guarantee holds no matter what you do. So wherever you stop, privacy guarantee holds. So with these two things in mind, now the question arises, which is useful? I don't have a very clear answer, but let's try to see. So there are two approaches which we designed. One is objective perturbation, another is OCP based. So objective perturbation requires stronger assumptions than OCP, this online convex programming, meaning that it requires the cost function. So in our work we allowed the regularizer to be non-differentiable, but it requires the empirical risk to be differentiable, and that we can prove that it is necessary. It's not a problem with the proof technique, it is necessary for the problem algorithm. But at the cost of that, you get better error guarantees. So it supports the structure of the problem better than what output or OCP does. Contrary to that, OCP algorithm is much more practical, in the sense you do not need to bother about whether the objective function actually minimizes or how good your, let's say, convex optimization package is working. You just take a bunch of outputs and take the average, and yeah, it is more meaningful. So I haven't pulled in output perturbation here because OCP performs unconditionally better than output perturbation with a polylog factor dependence on the dataset size, but that's fine. But it performs unconditionally better. So the comparison is essentially between objective and OCP. And
so you're comparing a batch algorithm with an
no,
online
this is a batch algorithm. So OCP is a technique I'm using for solving the batch problem. So let me make this clear. So I have a sequence of data points. So this is an online algorithm. OCP is an online algorithm. But I can think I'm pretending that the data points are coming online, but I'm solving a batch problem. So essentially, in the batch case, this thing works. And it so happened that people never looked at this kind of like using online algorithms for batch VRMs. So this talk so far, I've told you about in low dimensions 3 approaches: output, objective, and online convex programming, and give you a comparative study about each of the 3. Let's switch gears, and in this part what I will talk about is you want to do sparse regression in high dimensions. So the idea of high dimension is that the dimensionality of the problem is much larger than the number of sample points you have, and this makes the problem significantly challenging. Why is that so? So if we use the previous techniques, whatever I told you, output objective or OCP based, the error scales polynomially in the dimensionality and one by sample size. But I told you that the dimensionality of the problem is significantly higher than the number of samples you have. So to get any consistent estimator, you need to control this dimensionality, the dependence on the dimensionality significantly, and what you want is something like logarithmic in it. What you show is, in the high dimensional case, for sparse problems and specifically for linear problems, the error scale is polynomial in the logarithmic of the dimensionality, polylog of the dimensionality. And to do this, we assume that the underlying model parameter we are trying to learn is sparse. Sparse meaning it has very few non-zero entries. So just digging a bit deeper in what sparse regression is. So the number of dimensions of the problem is much more than the number of samples you have. So if you look at so essentially what you are doing in empirical risk minimization problems, we are solving some kind of an objective perturbation, objective function. We are kind of minimizing an objective function. Now when the dimensionality of the problem is much larger than the number of sample points you have, the objective function will look something like this. You can assume it to, I mean, you can view it as a boat where there's a lot of flat point in the middle. Now any of the model parameters here will work equally good on the dataset, but recall that your idea was to work on a new sample you get, not on the dataset. So for that you need to choose the right model parameter, and if I just give you the problem in its original form where you have the dimensionality larger than the number of samples, the problem is extremely underdetermined. So how do you go about it? It so happens that statisticians saw that if the underlying model parameter which you are trying to learn is sparse, sparse meaning it has very few non-zero entries, then you can actually search for parameter vectors which has this property that they are sparse. So in that case you can constrain your search space significantly rather than looking completely here on this line. And this, from a computer science perspective, so this was done mostly by statisticians. From a computer science perspective, this is essentially a feature selection problem. You are given a bunch of features, you want to select a subset of features which are useful for you, and this is essentially a feature selection problem. So for doing this, we designed two algorithms, and both these algorithms have a very similar flavor. What you do is, first you run an algorithm to select a bunch of features. Then in the second stage, we use this idea of objective perturbation. First you select the features, restrict the problem to that small subset, and use objective perturbation restricted to that set, because now we are in the low dimensional setting once we get the features out. And for doing that, we use two approaches. One is this exponential sampling based algorithm, which is roughly based on some of the ideas from Maxeri and Talwar in 2007, and another is a subsampling based approach which loosely relates to the idea of sample and aggregate framework from Nissim et al. In 2007. So in this talk I will be specifically speaking about subsampling based approach, because this guy is in some sense a first cut solution which you get, and this is in some sense it is not computationally efficient, but this is a computationally efficient algorithm, and this is what I'm going to speak about. So what subsampling based algorithm does, you take the complete data set, break it up into blocks of root n size, the data set, run your favorite feature selection algorithm on each of the blocks. So each block gives you a bunch of features which it thinks is to be important, and from that out thing you take a noisy vote. So how you take the noisy vote I will tell you. So this is at a high level, so you can plug in any feature selection algorithm what you want. It is essentially oblivious to this. So suppose block 1 comes, it votes for a bunch of features, s number of features it votes for. Then block 2 does the same, and block root n also does the same. Now what you do is, you take the votes for each of the features which has got from different root n blocks, add noise in the order of s by epsilon to it, and give the block out. Sorry. Yeah. Now this is the noisy votes you have. You select the top s in terms of these noisy votes, and the claim is that this guy is differentially private. Yeah, sure.
What do you mean by each count?
So So these guys vote for it, right? So vote is like +1 or +1 or 0.
Yeah.
So this guy will have bunch of votes.
Also, the count that it already has from already.
Yes. Count for the votes. Yeah. No.
When you say add noise,
Add noise in the sense, oh, so yeah, there I was kind of sloppy there. Add noise essentially you add scaled Laplace noise, where the scaling is S by epsilon.
when you say that the result of the voting is differentially private, I mean, you're not actually exposing that, right?
Yeah, I'm exposing. What I'm exposing is the coordinates, which I'm choosing. So that can be shown out to the world that this S coordinates is the thing which I'm reducing the problem down to. And this is differentially private, epsilon differentially private. So what we do is we use this generic thing and try to study it under linear regression. So in linear regression, what you have a design matrix and a model parameter, which is n cross p, and an additional field noise to it. And the response is y. So this hatched parts, you can think of personal information about a person. This is like whether he has AIDS, and this is the Fisher vectors. The way you solve a linear regression problem is you want to find out this theta star. And what you want to do is you want to minimize this objective function, which will give you an estimate of theta star. So the minimization is the gap between the L2 norms. The L2 norm of the difference between y and x theta, plus some appropriately chosen regularizer. For different problems, you choose different things. So for lasso, there are different variants: lasso, regression, etc. So in the typical settings of theta star, the underlying model parameter, design matrix, and the output vector, the exponential sampling base requires around s cube log p number of samples. And the subsampling based algorithm which we have requires s square log square p number of samples. If you note, both algorithms have sample complexity of poly s log p. So I have pulled down the sample complexity from p to log p with a polynomial dependence on the sparsity, but that's fine. So now if p grows faster than n, still I will get a good convergence rate because n just needs to grow in log p. So this bypasses some of the impossibility results in the literature, which talks about deterministic algorithms may not be differentially private. But since we are working with randomized algorithms, it's fine. So I'll not go into the details of it. Yeah, so this talk so far: low dimensions, output perturbation, objective perturbation, online convex program. Sure.
Did you assume that S is square root of n? Or
S is smaller than n.
Sorry?
S is smaller than n.
Smaller than.
Smaller than
But
n.
there's no requirement on being square root or less,
No,
right?
no. So in the high dimension, we need we have the dimension of the problem larger than the entries, and we give a differentially private sparse regression. By the way, you should tell me when I should stop. Yeah,
So
sure.
The S was the number of non-zero
Entries in the underlying parameter. So this guy, number of non-zero entries in this person. One very common example people use is, suppose you are taking photos of stars on the night sky. Not every place you will find a star. There are very few places you will find a star. So you can actually see that you can use the model which you are trying to learn. You can assume that there are very few entries which are non-zero, and that's essentially they use in astronomical data. They use sparse regression quite a bit. Yes. So I don't know. Have I gone over time? Not time. So I can stop at this point also. Huh? 12:30. Yeah, sure. I'll go, and this will take another 10-15 minutes, I guess. So yeah. So after having talked in this problem for the problem when you have samples in batch, now I'll tell you how do you do it in online when the samples are coming to you one after another. So the data points are equivalently the cost functions, as I told you in the how do you map it, arrives to online. And in this setting, so this is a work with Prateek Jain, Pravesh, Kothari, and me in Cole 2012, where we give a very generic transformation. So I'll give you an OCP algorithm. I'll plug it into the system. The system will give a differentially private variant of it. Moreover, if the original OCP algorithm had sublinear regret, recall the sublinear regret was how do I perform well with the best possible offline adversary. The private version will also have sublinear regret. And additionally, we show that if the loss function has some properties like it's a quadratic loss, like linear loss, then we can get private variant with almost optimal non-private regret. So the non-private regret is around log t upon t, log n upon n, and we get almost close to that. So this is just a refresh of the OCP structure now in the online setting. Now we are actually working in the online setting. So there's a player, there is a challenger, player chooses a point in the convex set, the challenger chooses a cost function, you play a cost function, and you pay a regret at the end, and you want to minimize the regret. So the issue with online algorithms is this model parameters theta I when I was working in the batch setting, those were kept within the system, and at the end you take an average and give noise to output. But here you are outputting this model parameter at each and every iteration. So this is much more reactive compared to uptime in batch setting. You have to update the model parameter in each and every iteration. Every time you see a cost function, you update it and output it. And moreover, these cost functions can be containing sensitive user information. For example, for online classification, this can be the label whether a person has AIDS or not, and this is his feature vector. And you need to guarantee privacy across all the possible outputs. So the point is that if you have n data points, you have n outputs, and you have to guarantee privacy for all of this. And this is a pretty complicated task. I'll show you a toy attack, how online problem becomes kind of challenging. Suppose there is this adversary who is owner of some perfume brand. Let's call it ABC. And he wants to find out whether a person who clicks on his ad is a male or a female. So a male comes, clicks for writes perfume there in Bing. He sees this ad to be shown here as ABC. Now what he clicks on the ad, and the adversary gets the IP of the user who is clicking on it, and at the same time he knows that this guy has clicked on that. Now he wants to find out whether this person with this IP is male or female. Now what in the side of Bing, what Bing does is, Bing sees that a male guy has come, and for perfume he has clicked on this ad ABC. It might be that ABC should be re-ranked and given higher weightage. So the search engine upgrades this ad for all male users. This is a toy example, let me tell you. So Bing system doesn't, it's much more complicated than this, just an example. So this guy gets re-ranked. Now after the male clicked on the ad, the adversary immediately goes to his male profile. He had made a bunch of profiles earlier. He goes to his male profile and sees that for the male it has increased, and immediately goes to his female profile, he says that it hasn't increased. So the guy must have been a male. So the meta point is, online learning tends to make quick decisions. So every time you see some input, you make a decision, or you change the system, and that might compromise privacy. So the key thing what we did was, we tried to design online learning algorithms with controlled changes. So you do not want to make sharp updates with one single entry. And additionally, we added appropriate, so the idea was that when you output this model parameters, thetas, to the external world, we add some noise to it. Now this is a pretty common thing in differential privacy, everywhere everyone adds noise. Now what's the interesting part here? The interesting thing is, the number of inputs here is equal to the number of outputs. So you're not outputting a single thing, you're outputting a sequence of outputs, and that is exactly equal to the number of inputs you have, and it becomes significantly challenging to guarantee privacy in that setting. So the challenge is that privacy should be guaranteed across all outputs. Again, for privacy we use differential privacy here, so you want all the sequence of outputs to be differential private. So I should recall you the intuition here, because I'll tell why it is important. So the presence of a particular data point should not be visible to the observer, so the output should be kind of indistinguishable from the observer. And for online learning, we use this framework of online convergence programming here. So for doing the online learning, we use this OCP. So OCP algorithms usually have sublinear regret, meaning that as n goes to infinity, this guy goes to 0. Additionally, they have this property called as explore versus exploit. Roughly what explore versus exploit tells you is that when I see a new data point, I will explore that, but I will not discard what I have learned from the previous stuff. So that is the exploit part of the previous output. So this exploit versus exploit philosophy actually tells you that it does not allow you to make sharp updates. The OCP actually doesn't allow you to make sharp updates. And if you think now, the intuition for privacy and this explore versus exploit philosophy, these two are pretty much in sync. And in our analysis and proofs, we essentially use this idea. Although again, it is not clear to us that is it specific to online learning, this property, or is it, and it's more general in general learning scenario. Because essentially in learning scenario also you do not want to depend on one single point. We don't know. But for online learning at least this is true. So earlier, and in fact in the earlier talk I gave you a brief idea about what offline, in the offline when the batch setting what is there. So people had analyzed offline learning with privacy a bit, but this was not almost untouched in the online scenario. There's only one notable paper by Dwork et al. In 2010 which showed for online experts problem, a very specific kind of an online problem where you get sublinear regret, but that does not extend to general online convex programming, and there comes the challenge. Again, recall that the OCP algorithm we are dealing with, we want it to have sublinear regret, and it needs to be stable. Stable meaning that as time progresses, the dependence of that ith parameter should go down based on the data point of the cost function. So it should go as 1 by I. So it should go down significantly. Now, in the online algorithm, what we do is this: we maintain two copies of the model parameter. One we keep with the algorithm, and one we output to the external world. And the noise we add for outputting is roughly scaled around root I upon n. I is the ith iterate what I am outputting. So the model parameter theta is used for updating, and the noisy parameter which I am outputting to the outside is used for predictions. So what prediction I am giving. So that can be used by, let's say, by Bing to find out what next ad to show. Now for the privacy, the issue comes is that you have to guarantee privacy across all the iterations again. So there is this result by Dwork et al. In 2006, the initial paper on privacy, which tells that if I have a sequence of outputs, each of them is epsilon differentially private, then my complete sequence is n epsilon differentially private if there are n outputs. But that is not enough for us to get privacy here. I mean, get sublinear regret, because if privacy scales as n, then we can show that you will not get regret which goes down to 0 with n. So we needed a stronger composition result. So what we did was we kind of used the ideas from a recent paper by Dwork et al. In 2010 and Hart and Rothbaum in 2010, and we modified that analysis in our setting to get a composition result which roughly says that if I have sequence of n outputs, it's not n epsilon differentially private, it's root n epsilon differentially private, and that essentially allows us to get sublinear regret, coming back factor from n to root n. So we guarantee epsilon delta differential private algorithm for stable OCPs. The regret for the private variant is the regret for the non-private algorithm, OCP algorithm, plus a term O of log square n upon root n. So the regret scales as log square n upon root n, you can think of. So it is trivial to see that if the original algorithm has regret tending to 0, then the private one also has regret tending to 0. This is just a toy kind of scenario how it works. So this is model parameter. This is a learner, you can think it to be Bing, which is showing it output. The learner gets this. There is a trusted party which makes the computation. This user gives his user profile, like types of perfume and his user details. The system gives out an ad which is based on the user profile and the model parameter. This goes on, and based on whether this guy clicks on the ad or not, the system incurs a loss or cost, and this thing goes on for a bunch of iterations. So now what the system does is it updates to theta 2, but it gives the theta 2 with itself. What it shows is to the external world is something added with noise, and this goes on for theta 3 and blah blah. That's how it works. Coming to quadratic loss, if the loss function or the cost function is of this form, then we get our solution to have the, yeah, sure.
So when you say it updates according to the original theta 2, does it mean that in terms of raising or lowering the rank of the brand, will it actually use the true information? Or
No, it will use this for
it will use
the private version. So this is only used for the system for generating the sequence. Whatever you show to the external world is through this. So for the Yeah, for linear regression, we can get the regret down to log upon n instead of root n. Earlier it was root n, we get it for log by n. And for this, we heavily use the structure of the problem. And yeah, so this uses one technique by Dwork et al. And this is an improvement over 1 by root n. Yeah, so that's coming to the end of the talk. So what I've told you is, in low dimension, I have showed you 3 approaches to how to do empirical risk minimization in the batch. These 2 algorithms are the most promising ones. This one has better utility guarantees, and the online converse programming is more practical because the privacy guarantee holds at whatever you do. In the high dimensional setting, I told you about the first algorithm. So this is the first line of work for sparse regression in high dimensions, and I spoke to you about 2 different algorithms, exponential sampling best and the subsampling one, but I gave you the details of the subsampling one where you do this voting kind of a scheme, and the sample complexity scales as omega of log n. In the online thing, what I told you is I give you a generic framework how to translate your favorite OCP algorithm into a differentially private one, and I basically kind of hand waved at it to how to get tighter bounds for online linear regression instead of 1 by root n to 1 by n. So in terms of future work, in the batch VRM in high dimension, we have made some partial progress on that. So if you forget about privacy, the sample complexity required is S log p, but what you are getting is the best what you are getting is S square log square p, and our current analysis will not allow it to get down to S log p. The question arises is whether there is a gap between S log p and S square log p for the private and the non-private, which is whether that gap is necessary or we can actually breach that gap. So we have made some partial progress, and the short answer is probably yes, that we can bridge that gap, but it requires a significantly different analysis techniques. For online learning, if the cost functions, each of the cost functions, small loss functions what we had, if they were strongly convex, then non-private regret is known to be scaled as 1 by n, but our algorithm gives you 1 by root n. So the question is, can we bridge that gap? And that will be a significant improvement over this current algorithm if it does. In the long term, what we want to understand is the relationship between differential privacy and learning, because learning the whole intention of learning is to not to overfit your data to one single sample point, and differential privacy essentially needs that. So can we formalize that? And in learning, actually this notion is called a stability, and they have different variants of it. So can we actually formalize and give a deeper connection between that? And with that I want to end. Questions? Last comments?